Hi, everyone. Thanks for having us today. We are the Creighton University Blue Jays Go Green. We had the Ball State University district use case for the Department of Energy 2020 Solar District Cup. Just to introduce ourselves quick, I'm Nathan Adams. I am a senior at Creighton University, double majoring in financial analysis and sustainable energy science.
Hi, I'm Isaac Lampa. I am also a senior at Creighton University, and I'm double majoring in sustainable energy science and physics.
I'm Bridget Slavin, majoring in sustainable energy science with a minor in business.
I'm Logan Smith. I'm a junior at Creighton studying sustainable energy science with a minor in theology and sustainability.
So first of all, we want to thank the Department of Energy for allowing us to be in this competition. It has allowed us to build experience and develop some real-world solutions that will shape our careers. And we hope to shape Ball State's future as well. The overarching goal for our team was to assume the role of renewable energy developers and design a solar plus storage system for Ball State that maximizes energy offset and financial savings over 20 years. At the beginning of the project, we wanted to make sure all options were explored. Ball State's main campus, which was on the space provided to us, is shown in the figure at the top. Along with that, a northern section of campus is shown in the figure to the left, with each of our teammates bringing us different skill sets to the table. We were able to push through the challenge of this competition. Our team approach was to be a cohesive unit, which is why we had 90-minute team meetings twice a week and created 4 subcommittees. The focus points of these subcommittees were conceptual system design, distribution system impact analysis, financial analysis, and development and construction. Communication through the GroupMe app was very helpful during this time, and even more so when the pandemic closed Creighton. Not being able to meet in person hindered our progress, but we overcame that and adapted to the situation. We held meetings through Zoom once a week, and the subcommittees continued working.
It is important to recognize the need for synthesis when there are so many moving parts that needed to come together. A continuous reiteration of goals and constraints from conceptual system design, site development, distribution system modeling, and the financial analysis created a robust study of all the topics discussed and how they relate to one another. Each team, characterized by each of these topics, had their own resources and technologies that would help exploit and synthesize the goals and constraints of that topic. Later, a synthesis of all topics was created to produce the final solution. Each team member presented to the rest of the group as a competency check to ensure the understanding of these critical topics. For topics we didn't understand readily, the team sought the advice from 3 Midwest sustainable energy companies. We even invited representatives from Omaha Public Power District to actually agree to support our travel to Atlanta to consult on battery analysis and value stacking at a utility scale. The advice from industry experts was critical to the creation of these proposals. For the proposed projects, Blue Jays Go Green is suggesting to proceed with a phased approach.
So to keep options open for Ball State, we created a phased solution. The phased approach enables Ball State to make incremental additions to their systems and to add resilience and environmental value. This allows developers to build credibility and for the stakeholders of Ball State to see the value in each of the systems built. This figure shows a zoomed out version of where we are proposing our solutions, with phase 1 on main campus and phase 2 just north of campus in a large field. So phase 1 contains rooftop PV systems on 4 green tier buildings on Ball State's main campus. We will explain the green tier terminology later in this presentation, as it was one of the analysis tools we created. The total nameplate capacity of this first phase is 1.48 megawatt DC and includes 5 Tesla Powerwall 2 batteries. Phase 2, which would begin after the completion of phase 1, contains 2 field arrays that take advantage of single axis trackers. The total nameplate capacity for this energy system is 4.55 megawatt DC and includes a Tesla PowerPack utility scale battery. After our distribution system impact analysis, however, we discovered Ball State doesn't have the infrastructure to handle a large system in the north field. So we modeled running a transmission line from the proposed array back to the distribution line. We estimate an added $800,000 to $1 million upgrade is needed before this large of a system can be fully utilized. And in our written proposal, we have a variety of other system proposals that includes the architecture building. We discuss those in our documents, so we'd be happy to answer more questions on those later. So our methodology for this competition utilized a number of resources and tools, including Helioscope, Aurora Solar, the National Renewable Energy SAM and REOP Light tools, as well as OpenDSS and SketchUp to do our feasibility analysis. And these figures of the David Letterman Communications Building are just an example of the respective shading, generation, electrical, and aesthetic models we created for each building in the space provided, just to hit all the bases. So along with these tools provided, we also created and utilized our own analysis tools. One of these was a building feasibility score matrix. We created this in Microsoft Excel, and the resulting matrix is shown in the figure to the left. This matrix was created to isolate BSU's campus on a building by building basis. The algorithm for the matrix pulled from generation potential, shading analysis, and aesthetics. And after our fatal flaw analysis, 4 buildings were identified as these green tier areas for solar PV systems and are highlighted in green in the figure to the right. These are the best rooftops available for solar PV systems: the Robert Bell Building, the David Letterman Telecommunications Building, the Whittinger Business Building, and the Music Building. During our fatal flaw analysis, we also considered the Neuer complex, but ultimately decided to not include it as an option for green tier ranking.
We used REOP Light to determine the sizing and the function of the battery storage system for Ball State. The software recommended using small scale batteries for phase 1 and utility scale battery for phase 2. The energy capacity of the proposed batteries in each phase are listed here. The REOP models guided our team using resiliency as an important factor for our proposed system. Although the phase 1 storage is only 35 kilowatt hours and is not enough to supply Ball State with an hour or longer worth of energy, the capability to cover momentary interruptions can save a consumer like Ball State thousands. Using the interruption cost estimate calculator, which was a resource recommended to us by Omaha Public Power District, and is calculator used on large scale resiliency values, it was determined that a consumer like Ball State could save roughly $13,000, and this is according to the Berkeley National Laboratory. And these savings multiplies per event, and Indiana Michigan Power reported 6 major events in the year 2018 alone. The primary design constraint the team was tasked with was overvoltage, and we needed to figure out a way to ensure that our conceptual system design would not lead to overvoltage anywhere on Ball State's grid. The methodology used to prevent overvoltage on the green tier buildings identified was to size the PV and battery systems to never produce more electricity than the building which they would sit upon. This would allow us to not worry about overvoltage and then focus our attention onto resilience and financial optimization. The system sizes in phase 1 were input into OpenDSS. Figures show one of the 3 phases of the transformer on the Robert Bell Building for 2 days. As shown for the PV and battery system, they will not lead to covering all of the energy used at any given time, and this allows us to move our design forward without voltage violations. Also on the graph, there's a spike in usage, which occurs every weekday at 6 a.m., and our team found out that this spike falls outside of the demand charge billing time, which is 7 a.m. to 9 p.m., so our system was not optimized to worry about this peak. And in our documents, we provided some behavioral changes that could be implemented to account for this peak, and we'd love to answer questions on those. This slide moves the scale from 2 days to a month of usage at the same transformer shown before. And this allows you to see the shaving which occurs following that 6 a.m. peak on a much larger scale. And lastly, when running OpenDSS models, we never saw voltage vary more than 1% at the substation, which indicates no voltage violations occurring.
So through the development plans, it was determined the proposed project will take up to about 1 year and 4 months for both phases, and only about 1 year if BSU only chooses to go forward with phase 1. Keeping in mind this is a university, most construction is scheduled to be completed by late August when students start moving in and classes begin. Also, this schedule was created to allow extra time for any delays on permits, design approvals, and any weather delays during actual construction. Some specific permits will be needed before BSU can begin construction, such as a Class 1 structural permit and an electrical permit. While BSU is in a low flood risk area, an environmental engineer will still need to come visit the site just to ensure that the racking will not have to be raised or a berm will need to be implemented. While BSU isn't, the roof installation are proposed to be ballasted, while we are suggesting a single axis tracker to be utilized for the field array, but this will also depend on the geotechnical report that will be completed prior to construction.
So of course, we understand that any potential major projects, such as a solar installation, will need to be justified to Ball State University's stakeholders, such as the University Board of Trustees. We also understand that these stakeholders will be primarily concerned with financial feasibility. Therefore, one of the first things we did was we selected two metrics that will help us most effectively analyze and communicate the financial feasibility of our proposed arrays. As you can see there, the first metric that we selected is the net present value, or NPV. NPV is the long-term financial gain or loss of a project represented in today's value. Now, you can see down there below on the left that it is calculated as the sum of the present value of all future cash flows. For net present value, any positive value is a financial gain and any negative value is a financial loss. As we are utilizing two metrics though, it's important to note that net present value is our decision rule. The second metric that we selected is a modified internal rate of return, or MIRR. Now, a lot of people may choose to use a more traditional internal rate of return, or IRR. However, we found that inadequate because an IRR assumes that any cash flows are being reinvested at the IRR rate, which simply doesn't happen in the real world. Therefore, we decided to use a modified internal rate of return, which would account for funds and cash flows being reinvested at Ball State University's weighted average cost of capital, or their WACC. We found that this method rendered more accurate data for us to present to our clients. As can be seen below and on the right, our MIRR is calculated as the rate that equates the present value of all future cash outflows to the future value of all future cash inflows. We estimated WACC to be 8.42% for Ball State University. That was based on average university endowment returns over the past decade and the average bond market rates for the same period. You can see here our campus array phase 1 and our field array phase 2 were run through these models, and our phase 1 came up with an initial investment of about $2.3 million, a modified internal rate of return of 3.43%, and a net present value of a loss of $1.3 million. Our phase 2, which was our larger field array then, had an initial investment of about $7.3 million, a MIRR of about 3.35%, and a net present value of a loss of about $4.2 million. It is important to note that our field array there does not account for the estimated $800,000 to $1 million extra investment for needed infrastructure. Now, just because our rate of return does not match BSU's weighted average cost of capital does not mean that this is not a wise investment for the university. We've already talked about the value of resiliency, but it's important to note also the growth of goodwill that could result from Ball State taking a stand and becoming more of a green university. Finally, and most importantly, our plan and our arrays can offer consistent investment growth for the university. Endowments are not meant to be spiraling and jumping on their return rates. And over the past decade, the average university endowment returns ranged anywhere from 19% to -1%. That makes it very difficult for stakeholders to plan financially for important practices such as future projects, the implementation of strategic plans, or what scholarships are going to offer. While our rate of return is slightly lower than what their average would be, we can offer them a consistent rate of return over the next 20 years, meaning they can much more accurately plan for how much money they're going to have and how they're going to use that money to improve their university and the lives of their students.
So to reiterate, the first phase of our proposed solution is a 1.48 megawatt DC electric PV system with 35 kilowatt hours of storage spread over 4 buildings on Ball State's campus. Our phased approach enables Ball State to make incremental additions to their energy systems. We hope we are able to support Ball State with the information provided. For further specifications of the system as a whole, or for any information on further phases, we would be happy to answer questions. We also want to thank the DOE, the NREL, and all the judges for joining us today. Thank you for allowing us to present.